Thanks a lot for having me. It's really great to be here, and I did some preparation. So I bought this Amsterdam from Ian McEwan, but now I'm halfway through, and the word Amsterdam hasn't been mentioned yet. I don't know if you've read it, but at least I'm still working on it. No, thanks a lot for having me, and thanks a lot for making this possible. And we arrived safely over the weekend, and already Niels, my middle son, he is going to a school this morning. So we dropped him off. So he's going there for a few days. So let's see how it goes. So my phone is on, but
It's all being recorded.
It's all being recorded. Okay, well. Okay, so maybe we should get started. Yeah, quantum I/O. I wanted to have this as the title, but I think we agreed on quantum input/output for the archive paper. How to send and receive qubits with noisy devices. That's the topic, and it's a research program that I started with a postdoc, Alexander ller-Hermes, a few years ago. I'm very excited about it, and if you want to talk to me about it, I'd be very happy to talk. I think there's many kind of like ideas around in many ways in which we could develop it. Let's see. And even though we had this pre-seminar where you could have asked all the questions that you wanted, please do interrupt and ask the questions now, because the talk itself is kind of interdisciplinary within this interdisciplinary subject of quantum information. So, okay, here we go. Yeah, so we have this latest paper with a postdoc, Ashutosh Goswami, and with Omar Fauzi from Lyon, which is called Fault-tolerant quantum input/output. It's sort of set in a certain paradigm, and it's sort of in some sense developing further the work I have started with Alexander ller-Hermes, which is more focused on communication. So fault-tolerant coding for quantum communication. And with Paula Belzig, who's a PhD student in my group, also for another scenario with entanglement systems. Okay, so fault tolerance. So I find it a very complicated subject. So I'm sure for every aspect of my talk, there are some people in the audience that know more about it, and I will just guide the questions, I guess. So quantum algorithms. Oh yeah, I should also say, I have given this talk before at Quantinuum in Harry's group like a couple of weeks ago. So there are some jokes about that. Okay, anyway, so factoring. So quantum algorithms here, like, what are we going to do with the quantum algorithm? Are we going to factor some numbers? Okay, so Peter Shor showed us how to do it. 15, right? 5 times 3, 781. Now let's see if you're awake.
11 times 7. 11 times 11 times 7?
No. Yeah. No. 11 times 71.
Yeah, 11 times 7.
Okay. What are this one? Yeah. Okay. Let's see. Are you gonna do this? Okay. Here we go. Search. What about search? What we search? That's a phone number.
Check out.
Huh? Danish, right? That's me. What about this one? Harry? Yes. Very good. Yeah, very fast in search. What about this one here? I had to make it longer. It's kind of hard because the longest phone numbers are apparently in Germany. But what about this? Oh, yeah.
Joe Biden.
No, no, false. I don't actually know. I made it up in so maybe pretty short. All right. What about chemistry? So in chemistry, you use quantum phase estimation. You have some molecules. They might dock or not dock, right? So you put the input here actually for chemistry problem are the coordinates. You do the Born-Oppenheimer approximation, means the coordinates of the nuclei are the input to your problem, and then you want to compute the energy. And then, in dependence on the distance, you want to see if kind of like there is a valley, right, which it would dock or not. Okay. What do all these algorithms have in common? This gonna be, it's all recorded. They all have classical input and output. Okay. I think this is really quite remarkable, because if you as a physicist, you know, I think for computer scientists it might have seemed natural, and but for physicists that I never thought this was natural. So it doesn't really, you know, the world is quantum mechanical. Why do algorithms have classical inputs and outputs, right?
Because you're not quantum mechanical. You're not quantum mechanical. What are you gonna do with the,
Well, I'm quantum mechanical.
what are you gonna do? Are you,
Well, the
I
internet
think
is,
so, I mean, you know,
are you?
I think so. Otherwise, I would not be here. Matter would collapse, and I don't know. Okay, anyway, so yeah, so classical input output. So yeah, no, but if you take quantum seriously, I mean, there should be quantum input and output, I think. Okay, error correction, next topic. Error correction, okay. So you know that, of course, right? So if you have a hard time hearing what I'm saying, I'm just saying it 3 times. And then you do a majority vote decoding. And then Peter Shor, who of course was criticized for his Shor algorithm because it was not going to work, right? Because there would be errors. And he said, okay, let's just do this twice, okay, for the phase and for the bit errors and for the phase errors, and we get the 9-qubit Shor code. I was too lazy to put it in, so I have to cite Wiki for stealing the codes. Okay, and here is the encoding circuit, actually. It's taking the qubit in, okay, and then it's like doing C0s with those, and it does Hadamard, and then it does C0s with those, and then here you are in the code state, okay? If you put a 0 in, you get the size, the 0s, S I guess is for Shor code state, or the 1s code state. Then if an error happens, and that will be the decoding, but if an error happens, you can then recover it, okay? This would be the code. Just like before, you know, I had an error happen in the middle. If one error happens here, one of the 3 errors we discussed in the pre-seminar. Yeah. So, but what if the gates in the encoding or the decoding have an error? Right. So let's say the error happens. Yeah. So I should maybe say the word error correction refers to coding into it, then errors happening, and then you decoding. But what happens if an error happens during the encoding or the decoding? Then what can happen is that the error can spread, right? And then suddenly here, it's not a single error, but you have 3 errors. And actually, Shor code cannot correct for that. So the error correction could fail, and in this case, it will actually fail. So and this sort of like opens a new subject in the field, because in contrast to most coding classically, I guess most of the time this situation, you know, is not happening. The errors will happen only in storage or in transmission, but they will not happen during computation. In quantum, really, we have a hard time seeing that we will not have them during computation. And that is why we have to deal with them right there. And that is distinguishing the discussion of error correction from a discussion called fault tolerance. So fault tolerance, you want to have a construction that's tolerant to faults during the thing. So for that, we need to kind of like understand what we mean by a circuit. And for a circuit, we have a few objects. Normally, you would say like, oh, it's just like X, Y, Z, and a T and a C0 gate. It is good, though, to also have other options like having the identity as a gate, then preparing a 0 and preparing a 1, and doing a measurement also, and doing a partial trace as parts of your gate set. Then you write down your circuit in this. And if you want to make fault-tolerant constructions, then you do it in some way that every gate will be replaced by now a gate that you can do in your code, right? You will pick a code The Shor code's not so good for that. We'll talk about some other codes. But in any case, then on the code, you can run like some other gates on them that effectively then within your code space perform the right computation for you. So a good one to think about is the 7-qubit Steam code. And whenever you do such replacements, you'll get a bunch of complications in addition. So one thing that you want to do when you execute gates is the whole time you want to do some error correction, okay? So if you think of the whole time you're doing like everywhere during this circuit, you know, you always throw some error corrections in between and you correct errors on the fly the whole time. Okay, so and then your circuit basically blows up. Okay, so you start with your normal circuit and then you replace every qubit by 7 qubits and every gate you replace by these new gadgets in your code and sort of the high level way of doing it. Then you have to get into the code, right? And here we think of the here I wrote it down for you. That's the 7-qubit Steam code. Okay. It's a nice code because if you want to, for instance, know what the logical 1 is, you can just take, right, you do a bit flip on from a 0 going to a 1. It's just a bit flip, and so it is for this code. Okay, so you just have to flip all the bits in the code, and you go from the logical 0 to the logical 1. This is an operation called a transversal gate. Okay, so if a gate has the property that if you want to do something in your logical subspace, and then you just flip all of the bits. Here's, that's why I was lazy and not writing down the 1. Yeah, so we sometimes, now we're shifting the paradigm depending on which papers you look at, but they're basically Aleferes, Gottesman, and Preskill. They have a rather nice paper on fault tolerance, which sometimes I'm citing. So you take a gate and you replace it by this gadget, and that is what I just said. In the case of transversal gates, you have this nice structure that that the gate gets replaced by these really nice gates. There is another kind of important, and I use this symbol for encoding. Right, I think it's very natural. You start from the left, time goes right, and from 1 qubit it goes to many qubits. I will have tried to make some graphic notation to keep track of this subject. And concatenation is then this idea that you know, maybe once it's not sufficient. So you would really like to do it, and the effective every time you do a concatenation. So every time you do a replacement, what the code basically does is if you have a physical error at rate epsilon, then the effective after you've done the encoding, the error is only of order epsilon squared. Okay, so that's a really nice property of this code. So if you start with, you know, an error of 10 to the minus 3, then kind of it's going to be 10 to the minus 6 when you've done it. That's sort of the idea. But of course it's not going to be. There is a big constant in front of this, right? So typically, you know. You will have to do this probably in practice. You have to use some kind of family of codes of growing size in order to protect your information. Because, right? So you don't only want to encode it once. And a very nice way of getting a family of codes is to just take the 7-qubit Steam code. You do it once, okay, from 1 qubit to the 7 qubits, and then afterwards you do it again. So you take all of the qubits from the 7-qubit Steam code, you do it again. So you get 49 qubits. But the advantage is that so the number of qubits in the concatenation level grows exponentially, but the error suppression squares always. So it actually the error suppression is doubly exponentially fast. Some details, we don't need to do too much of it, but just to get you the idea. Okay? This concatenation is a very important concept, at least for what I will talk about. Okay. There's also decoding. I guess it just goes the other way around. Okay. Yeah, and then there is a nice theorem, and then I guess I take some questions after that. There is a nice theorem. So if you think about input, you should think about a big number, like in Shor's algorithm. Then you encode. Okay, so this is classical. Then you encode, you use these objects to encode. Then you run this encoded circuit. Okay, so like a Shor algorithm that you encode it, and then you decode and you get the output. It's sort of like a general structure of making a fault-tolerant quantum computation. And what's important is that the input here is assumed to be the classical, okay? So like in Shor's algorithm, the input is classical, the output is classical. Some big number, here are the factors. And in some sense, it's best if you think of it as being stable, okay? So it's like this classical information you have and it's stable. And as soon as you were to turn it into qubits, errors can happen. But there is a way of doing such a computation. You could also say like, oh, if errors happen, I'm assuming my classical information already comes in error correcting code. But I recommend to like just say like, hey, this is classical information, we assume it's stable. So this whole field of quantum computing, of quantum fault tolerance, still hinges on the fact that you have classical information that's stable. But I guess sort of like our daily experience with using computers and phones kind of like, you know, make us happy with that assumption. Then as soon as you've tried one of these online available quantum devices, you're less sure if that's also the assumption holds in the quantum world.
So
Yes.
in this setup, the assumption is errors happen only in this red region?
No, they can also happen in the encoding in the green part. They don't happen in the blue part.
So may I ask about the previous slide, this concatenation? So you said number of qubits goes up exponentially, error goes down double exponentially. How about the overhead to run the error correction procedure, so to say?
Or the overhead to run the error correction procedure?
Well, you're doing measurements and processing
Yeah.
syndromes. And is it getting out of hand, or is it?
No, I think that again depends very detailed on the architecture you're now talking about. On the level I'm talking about here, it's not a problem. But depending on which, so the error correction you would just do after every gate. So if you think about, you know, you replace a gate by some other gate, and then the error correction you just fire an error correction after that every time. So so yeah, there's a priori no problem there. But depending on the architecture and depending on maybe the model you're talking about, you could have situations in which the error correction will be a dominant part. But I think now for this it should be all locally defined. Yes.
So up till now, you've mostly been focusing on the case where you encode sort of one qubit at a time. Do you also consider the case where you might encode, say, multiple qubits at a time?
Yeah, but not during this. But in principle, you could do that, yes.
But does it tend to be better, or in practice, does it seem to be like just encoding one qubit at a time is the most efficient solution?
No. I mean, depending on what you want to do, encoding more qubits might be more efficient. But in terms of what I guess I want to do now, we usually take a single qubits at a time and encode them and decode them.
So like in your red box, it's not just kind of blowing up the gate into like implementing the gate with like, let's say all like X's or something, but it's also doing the error correction.
It's also doing the error correction. So you can say, every time I replace a gate by like some encoded gate, I'm also doing error correction afterwards. That's the usual setup.
And then like in these, when you encode, like you said, the errors can happen in these green boxes as well. Like is that?
Yeah, we'll talk. I will tell you about errors. Yeah, I will. I will tell you about. Hopefully, I will have something more on the error model. Yeah, here, you see they're happening. Yeah, okay, so you see that here. Did you see them happening?
Yeah.
So here, errors.
Same errors again.
Yeah, yeah. Even though I chose them random, it's amazing. Okay, so yeah, so what's the intuition that this works at all, right? I mean, there's no guarantee that any of this will actually result in the correct result. The intuition is that you do some kind of special construction where what I've shown you for the Shor circuit, for the Shor code, doesn't happen. Okay? If you don't want that to happen, right? You don't want the errors to spread. Because if you were to do that, then it would just not work. So you want to have some special construction such that the error corrections you have built in, and you built them everywhere in your circuit, that they somehow pull out more errors than they themselves introduce. Okay, because the error correction, of course, will also introduce errors. Not only the gates, but an error correction itself consists of gates. So of course, it will also introduce errors. Okay? There will be errors everywhere. So the procedure, the error correction procedure, of course, will not work as described, right? Because it has errors, right? You write down some circuit and say, that's my error correction saying it will not work like that. It will have errors on top, but it should be good enough so that you pull out with that half-working error correction more errors than you introduce yourself. Okay? And there are some constructions like that. And I guess for sort of like, if you want to be physicist there, then you're like saying, oh, I have to pull out more entropy, right? I have to pull out entropy. I have to cool the system. My error correction somehow cools the system, pulls away entropy. Yes.
So assume I write a very complicated quantum algorithm.
Yes.
So that would basically in your diagram mean that the orange rectangle has like a large length and a width, right?
Yes.
Then I would also need to scale up the height, like the encoding,
how much you encode here, yeah,
right?
yeah,
Okay.
yes.
To make it stable, because at some
That's
point,
right.
otherwise it will.
Yeah, you will see it in the next theorem there. I have a theorem listed. But the errors can happen here during encoding here, but they don't really happen exactly in the blue thing, but they can happen during kind of like the preparation. Okay, so there are procedures for preparing. There are procedures for preparing that are kind of like very good. Okay, so I can take a classical zero and I can prepare a very good logical zero state. Okay, in a logical logical. Okay, more questions about that?
Right.
Yeah.
Sorry, I got some more questions. Are you assuming random like distribution of errors? Or
Yeah.
they-
So here actually, I just
Oh,
gave
yeah,
as
no,
an
I see.
answer. So
I
the
see
errors
all the errors,
actually
yeah.
are, just assume them to be IID Pauli errors on the gates. Okay, so every gate. So if a gate is some kind of unitary, here is the identity gate. So if you have no unitary, right, then you can think of the now maybe, yeah, you can think of rho being replaced by 1 minus. Now I took yeah. So if I talk about errors in the gates, I call them delta. Okay, the probability happens with delta, and then with probability a third, I get either an X error or Y error or a Z error. Okay, where actually for the people who were in the pre-seminar, this here is called a Y error, and both an X and a Z. Okay. Or you can think that the qubit is just with probability delta is wiped out, or probably 4/3 delta it's wiped out and it's just replaced by that. And we're going to assume this like that it's IID. Just make it things simple, okay? But it's not going to be a tremendous simplification. And you can already immediately see why, because even though I throw the errors IID on the gates, because I'm running a circuit, the errors will be immediately correlated on the qubits after running for some time. Okay, so it's not sort of like these are not, even though I'm running them uncorrelated on gates, they're by no means like uncorrelated effective errors. They will be highly correlated errors throughout this circuit. Okay. All right. So here is a is a threshold theorem for
Yeah.
quantum computation, yes?
I still have a question about the previous picture.
Yeah,
So the green boxes on the right seem extremely fragile, no? Because you're sort of in the process of decoding, so your states are no longer protected.
yeah,
Errors are happening there.
yes, yes.
Is there an alternative where there's like a notion of fault-tolerant measurement, where you don't unpack the logical qubits, but instead you?
Yeah, that is kind of what's happening here, actually, okay? So in these boxes here, it is actually happening. These are somehow, you can think of this here as a fault-tolerant measurement, because the output here is just a classical bit, right? So this is a fault-tolerant measurement, and this here is a fault-tolerant encoding of a classical bit into the logical thing. So this is a fault-tolerant state preparation.
Is the error on the output bits now sort of lower bounded by the probability of an error in the green boxes on the right or not? Or is it better than that?
No, it's better than that.
Better than that?
It's like, there's no error.
Like you could measure just
Yeah.
a string and then decode that classically or say.
Yeah, you can, yeah, you could assume that you have, yeah, so classically you can do classical arithmetics, yes. So you can do like, you can do like, you could like do this several times, but the better way to think about it is that I have a fault-tolerant procedure to making this measurement. I think that's the, so you can do a fault-tolerant state preparation and you can do a fault-tolerant measurement procedure there. Yeah. Yeah, but if you want to think like, oh, there is an error happening, then you could also like just repeat it several times, right? And then you and then somehow do some kind of majority vote at the end. But I think it's better to think about I'm doing a fault-tolerant measurement. So here's this threshold theorem. It's now, I mean, there's some history to this, etc. I'm not going into the history, but Alifers, Gosman, and Preskel have a very nice kind of like rather rigorous statement of it. And that's why I'm, the subject, maybe I should say that the subject in general is kind of like complicated because it's simply on the way the literature is written. So if you're reading through this literature, it has different levels of rigor. And that alone makes it hard to at the end combine it into say a theorem. Okay, if you want to, it's very hard to like take things from here and there and put them together in theorems because they don't come boxed up like we're kind of used to it from quantum communication or from quantum algorithms research. It has also heuristic parts that kind of research. So it's actually a bit of a challenge there. But anyway, Alifers, Gosman, and Preskel 2006 have a very nice thing. And what you want to have is this, right? You want to, here's your Shor, okay? And you want to have the Shor, you want to have this fault-tolerant machine producing the output of the Shor, okay? And the question is, you know, what do I have to do? So there is a threshold, delta 0 for this gate noise. So that's what the statement, what the theorem says, that if you put yourself below the threshold, a good way of thinking is that you put yourself like at a half times the threshold. Okay, so threshold is 1 in 1,000. You put yourself at 1 in 2,000. Okay, the error happens at 1. Then there is a threshold such that for all deltas, okay, take it to small enough, for all circuits and inputs, okay, and then you want that the probability of the output of the, so, you know, I told you the levels of encoding of the K level at delta noise. Okay, so this is the output of the left. You want that and then this here is output at 0 level and 0 noise. That's the original circuit. You want that the probability of these two things is not very different. Okay, so you want that the output has the same, it's the same for this one, right? You want to get the same number. You're happy if it makes a small error, but not too much. And now the argument basically is some kind of union bound. Okay, so the proof kind of like does a union bound. That means the output here, it scales with the number of gates you have in your circuit. And then it has this doubly exponential error suppression with the level K. So if you take now delta to be a half times delta 0, then it says here a half, right? And then it's 2 to the K. So a half times to the power of 2 to the K. So if you take this this K to be say logarithmic in the number of gates, then this here it's then it's a half to the number of gates, right? So this already, you know, dumps any polynomial you have. So if your circuit is polynomial size, any polynomial, and I put k to be logarithmic in the size of the circuit, already this here will be, you know, exponentially small.
Sorry, could you repeat?
It's double logarithmic.
Even double logarithmic would work, yeah. But, you know, yeah. But then it would not be exponential somehow. But yeah,
But you can make it smaller than any
Yeah.
polynomial.
you can make it small then.
And if you pick your k log number of qubits,
Yes.
then the overhead is only polynomial.
Yes, that's right. Yeah. So that's great, no? Fantastic theorem.
Well, sorry, what is K?
Yeah, so take K, okay, so take K, so if you want to have a simple computation, you take K to be logarithmic in the number of gates.
What's K stand for? It's the level.
Okay, was the level of the encoding.
So
You know, how often,
concatenation.
how often do I do the, yeah, how often do I do the concatenation? Ah, yeah, so I can take, yeah, I actually don't want to take it, yeah, so I want to take a double logarithmic. So I want to take it, so take K to be, that's right. So take K to be, you know, order log number of gates. It's a very small number, okay? But in practice, you know, it has to be kind of,
Sorry, you said this, does delta zero depend on the circuit?
no, delta zero is fixed. Delta zero is fixed, some number.
Well, what is model?
Depends, oh, but I fixed the error model. I showed you before what it was, right? That was the error model.
The hardware gives you delta zero.
The hardware gives you delta zero, yeah.
So you could kind of keep running an arbitrarily long.
Yes. Yeah, I have to. Well, I have to adjust my K, right?
Right, that's what I was
My
expecting.
encoding.
I somehow didn't see it here, so, oh, wait, oh, I see.
I have
that's why it's
to,
number
I have to
five.
adjust the K, the level,
Yeah, now I see it.
to the size of the circuit, but not really to the. So this is just basically, I make this encoding so high
You want it to be
that
like 1 over number of gates.
Yes.
Yeah, I didn't see. that.
exactly. I want to have the error per gate to be very small so that I can take this union bound later. Yes.
Does it make a difference whether you have like the gates in series or in parallel?
Yes, you want to do stuff in parallel as much as you can. And you also have to do certain things in parallel.
But this analysis just counts the number of total gates, right? It doesn't make any like analysis of the depth of the circuit that you're running.
Yes, but you saw my construction. So the construction will somehow preserve, right? The construction preserve the structure of the circuit.
Why do you want to do things in parallel?
Um,
Because I mean, at any time, the probability of error must go up with qubits because each qubit has an independent probability.
yeah, I guess it also depends a little bit on your noise model and how you adjust it.
Oh, but I guess actually even the identity is a gate, so.
Yeah, it depends
somehow-
on where you put your error model now exactly. If you want to have gates there for the weighting.
But I think in a series computation, the probability that error propagation should be more severe, right? Like
Yes.
Not
Yeah. I mean, but basically think of this, I mean, the construction I'm giving you now, okay? It preserves the structure of your circuit, right? The circuit, and then you kind of like put it there and you have these error corrections all over. Yeah, does it make sense? But it's true. I mean, there's many results in error correction and how this has to work, etc. But maybe we'll, yeah, we can talk about that.
What happens if you go beyond delta zero?
I mean, then the theorem just doesn't have a guarantee, right? It just says there is a threshold, and then I mean, then there should be if you're going too high, then then your error correction does not then your construction doesn't work, right? It has to suck out more errors than it introduces, and then it will just explode.
Yeah,
I
so
think
very
it will
quickly,
just,
as soon as you.
as
go
soon
to
as you
cycle-
cross, you should, yeah. But what people do in practice is basically also they estimate the delta zero with numerics. So, right, there is the question, what can you prove? But then there might also be the thing that you observe in practice. Because when you prove these things, then you get like really stupid big constants, right? You do some kind of union bounds and counting and so on. And that's not at all what happens in practice. Practice is usually much better. So there's a number of studies that show what the errors, what the thresholds are, etc. You happy?
Just wondering, what are the current best estimates for the threshold? Is it like-
Oh, it depends on your model, but I think there are people who have, there's results in the, you know, percentage range, bigger than that, depending on your model, yeah. So, yeah, but the overhead in the constructions usually tell you that you want to be significantly below what your threshold is. Otherwise, the overheads in the constructions are very high. But this year, we're using this kind of thing because we can prove stuff, not because they're particularly good in terms of like what the numbers are that come out. Okay, so hey, let's go to the quantum part. How much time do I have? Yeah, so you saw the whole thing was classical input output. Now we're going quantum input output. What if our noisy device interacts with the quantum black box? So, and as you know, I gave this is a picture of something that people in Copenhagen build, like that I work with. Like this is some kind of like, you know, neutral atom array. And this here is one of the Quantinuum chips, okay? So what happens if you want them to interact, right? The one guy does something and gives the qubits to the other one. It's supposed to do something and back, right? Doesn't fit into the model in some sense that we discussed. Well, we need to distribute, you know, what if we need to distribute the computation to computers based on different fault-tolerant architectures? Right? I guess I would maybe argue that this isn't fault-tolerant at all, but okay. But what about, you know, this is actually, I think, an IBM chip, and these are the two different chips from Quantinuum. So what, and they maybe have some in the future, some fault-tolerant architecture, but maybe it's a different one. Okay, one runs the surface code, the other runs concatenated code, or I got no, I don't know. And what if the noisy devices, they need to communicate via realistic communication lines?
So sorry, for the middle, do you mean that like there's some computer in one architecture
Mhm.
and it has some encoding and you want to switch encoding?
Yes, for instance, yeah. Yeah, what if the noisy devices need to communicate via realistic communication line? So let's say I have these two devices, maybe they're even the same, but they need to communicate via some kind of realistic, you know, fiber. Okay. Then suddenly I need to think about what to do. It's not obviously fitting into the model. Yeah, what if, now I'm abstracting the questions, what if we need to receive quantum information? Okay, so we could of course say, well, I want to receive quantum information. Well, I mean, I want to deliver it, please, in my favorite quantum error correcting code, right? Of course, great, I can say that, you know, but it puts the burden on the other person, right? And what if we need to send quantum information? I could say, well, I mean, you know, I just send it in my favorite quantum error correcting code. Puts the burden on the receiver. So someone needs to solve the problem, okay? So someone needs to solve the problem of this quantum input and output. How do I receive, you know, and send stuff?
So like you can kind of get a state out of your black box, but the idea is like it will immediately be noisy, but you could get multiple states out and you somehow want to turn that ability into being able to code it or something.
Yeah, so I mean, basically, I'm not making this too precise now, right? So maybe I'll give you a theorem in a minute, but just so like the idea is like, okay, I want to, you know, I have a quantum machine. I want to interact with this other quantum machine. Yeah, what can go wrong? Like, okay, what should I do if now my code is surface code? Yeah, I will have to talk about the interface, right? I will have to somehow talk about like, how do I transform that code? into something I can give to you, or I have something intermediate. Usually, probably will have some intermediate carrier, say photons. So I have to kind of like encode it into photons. Then there may be some noise happening, and the other person has to receive and put it into the code. So if I'm serious about connecting somehow quantum computers and not just giving them classical information, then I need to start thinking about this. Yes.
Is the problem like only appearing if you want to switch between codes, or is it already like, because I can imagine, an obvious thing would be like, okay, I get a qubit out and it's, it's not a classical bit, it's a qubit.
Yeah.
And then I say, oh, I'm just going to encode it in my code. But somehow that problem is that it's already, like, that doesn't work.
That
right?
doesn't work, yeah.
So that's already an issue.
Yeah, exactly. So you already run into a problem because, maybe I cut that out before. It took me many years to understand. It sounds completely trivial, but if you have a qubit, and it's not in a code, okay, say I have a qubit here, it's not in code, then I cannot protect it from errors. Okay, so because imagine I'm like, oh, I get this qubit here. Oh, yeah, no problem. I'm just getting encoded now in an error correcting code, right? But then with the probability delta, the first gate will make a mistake. And so my qubit will have a delta error on top of it immediately. Okay, before, first time I touch it, it gets a delta error.
Will you know if it gets the error?
No, I don't even know if it gets the error, right? But with the probability delta, if I have n qubits, then I know that a delta fraction of them will have an error. Which means that if I wanted to prepare some kind of state on n qubits, well, I mean, fidelity would be 0, right? Fidelity in a product with the state I wanted to prepare is 0 immediately, I mean, exponentially small.
Can you ask for parallel copies of the state?
No, necessarily, no. Why should I?
Yeah, but
Why
I'm
should I
just
be able
wondering,
to?
so then it
I
seems
can
like-
only do that, right, if I were in a model that someone prepared this, it has some classical data and prepares the state. Then I could ask for it multiple times.
But so you're really like, you get one qubit out and it's immediately going to start having errors as you wait for more copies.
Yeah, so you see your problem.
Yeah.
The problem with talking about quantum information is that if you're in a noisy environment, you can't even do that, right? You have to at any point somehow hold the quantum information in some kind of code.
So you'll, as it comes out, start trying to encode it, and then you'll somehow combine these things, knowing that.
Yeah,
some
maybe,
kind of delta
okay, so
function
I can tell you a little bit, so I just, yeah, let me, so you cannot, if I have this perfect, like, great information, right, great quantum information in my code, then, but you have a different, you like stuff in different codes, right? The natural thing would be to decode it and then to encode it in your code, but that doesn't work. Because once I have the bare qubit sitting there, in that moment, an error might happen with probability delta. And then, my whole error suppression like went haywire. Okay, so I really need to think about what do I do with quantum information, passing it on from one person to the other.
But I guess it's even more complicated because there are like 3 codes. There's the code of you, there's a code of me, and then there's another code for the transmission channel.
Yeah, then maybe even that situation, yeah. But yeah, so there are many problems here. We don't know how to solve all of them right away, but we can do something. So here's a statement for sending quantum information that we can prove. Let me see. So let's say you want to, okay, hold on. Let me see. Let me start here, I guess. So you want to prepare some quantum state, okay? In some circuit, prepare some quantum state upon input 0. It's here. And now you want to kind of, and maybe lies on n qubits, okay, yes. And now here is a procedure you could imagine doing. You start with your 0, then you do this and you do your circuit just as before, okay? So this is your encoded circuit. And then you're like, okay, here I stop. Well, great, no? Now I have prepared it. This is the most natural thing you might think about. You prepared it in the logical subspace, right? So why was that? Okay, so what's the problem with that? Too many qubits, okay? The left has like too many qubits, right? It has like, you know, I don't know, more qubits, right? If I do it, maybe 7 times more if I do it once, or 49 times more.
You only blew it up by a factor of like, this K was only like log number of gates.
Yeah, I didn't blow it up by much, but let's say, you know, my, you know, I can only use my, I'm gonna, you know, I have to produce a state and I have to do something with it. I have to give it to someone, okay? And I cannot just, you know, I have to, you know, I cannot just, the person doesn't accept, you know, the person doesn't accept the 49 times blown up circuit, or it doesn't accept a code of this type, right? Then that's not good enough. So I could say like, okay, so let me decode it. This is something that we just discussed before. I could just decode it. Just let me try to decode it. And then I have the right number of qubits, right? And now I really decode, and don't do a fault-tolerant measure, I have the right number of codes, but qubits, but errors could happen here at the end. So at least a delta fraction of the qubits will be hit by an error here at the end. And basically, but so it will never be of this form, right? It cannot be cannot have produced this. But what it, okay, or maybe without errors it would have, okay? So without errors, when I do this procedure, it would actually produce this. But now if errors happen, then at least, yeah, you see somewhere there in the front, see? Some delta fraction of errors happened here. But what we can show is that this is sort of the worst that happens, okay? That you have errors at the end. Okay. So the theorem says, if you want to prepare a state, you can successfully, with this construction, prepare the state, plus it gets some low weight noise to it. And we can talk about the details of what this low weight noise is, but it's essentially that the delta fraction of the qubits have an error on it. Okay. And what I was trying to say is that you cannot do better than that. Okay, there is no procedure that will do better than a delta fraction of errors at the end, because in the very last step, okay, just before you get the hands on your qubits, this error could happen.
I'm sorry, are you doing this just for the compression? You don't want to send the physical qubits in the encoded state when?
Yeah, so for instance, it could be that, yeah, so this is somehow the subroutine, right? And then we can try to use it somewhere.
Sure.
Okay, so state preparation subroutine. So for instance, if the state that I'm preparing could be the code state for some communication code.
The communication codes, they differ. Why? I mean, I still don't know why do you send physical qubits? What's the problem?
Sorry?
Why don't you send physical qubits and like why don't you stop at red? I mean, what's
It depends what I want to do with them, right?
Yeah.
But certainly the question then is, what is my statement? So on my,
Well,
in my
yeah, I
task,
guess nothing non-trivial. It's just write it down.
but it depends what you want to do with it. So you send it to whom? Or you send it
We
to,
should send the physical qubits by communication channel. I mean,
Yeah, yeah, I can do that.
You have to deal with the conversion, I guess, to photons or something. That would be appropriate and trivial.
yes. No, of course, there's nothing wrong. There's nothing wrong with that. It's a question, I don't want to do that, right?
Why not?
I mean, this is just, you know, of course I could do that, but what do I mean, now the statement is now if, like, this is maybe encoded in my Steam code, right? In my 7-qubit Steam code, but you know, I want to give it to someone who's got an IBM machine.
Yeah.
And the IBM machine runs a surface code, not a Steam code, right?
He wants a statement that's independent of the code. You can imagine attaching these encoding triangles at the right side of this blue circuit there. But then these would be approximately equal, but then I guess the statement depends on the code. Like when you decode it, then there is.
If you want to do it in a hardware efficient way, then maybe. But if you have a universal device, then you can compute in a different code. Why not?
Maybe it helps you just to think of it that I have a state preparation problem now. I'm supposed to prepare a certain state on n qubits, right? And how do I do this, right? So I want to prepare that state here. And with this construction, I have not succeeded. Okay.
If you want that, then
Yeah, so that's what I want.
Well, okay, but you have, I guess, like in some basis you have also succeeded, right? You could say that about any code.
No, it's actually not, it's not obvious because if you are in a logical subspace, doesn't actually mean that you are in a subspace. So there will be errors on top, right? It's just that the errors are correctable.
I see, but they're not corrected necessarily.
They're not necessarily corrected. And if I were to correct them, I would introduce errors.
So is it like, because you can't sort of, like, if you would produce the state, as you say, it would just immediately have errors. So you don't want to produce the state, but you're trying to come up with what is the thing that you want.
Yes. Yeah, let me maybe continue a little bit and you see how I want to use it, okay? So for the moment,
Before you do it, just a quick question. Do you know if it's possible, this is a mathematical question, do you know if it's possible to recompute a code from one encoded space, like sorry, from one code, sorry, I'm saying it clearly. Do you know if it's possible to recompute the state, to re-encode state on one device from one code to another in a fault-tolerant way without going through the sieve somehow? Do you think if that's possible? Because that would be interesting, right?
like a code switching for arbitrary codes.
So, yes, yes.
I don't think that's
But for some codes, it's possible to do code switching.
for some codes it's possible.
Okay, thanks.
But we wanted, maybe yeah.
Yeah, thanks. No, that's
I can roll up the, okay, so the way I now presented the results is somehow, okay, there's other option of doing that, but so what I want, so what I was gonna tell you now is, so we have this theorem, it's optimal as the errors can happen in the end, okay? Another thing that's interesting about the theorem is that we have it in two noise models, and one of them is, or what's interesting is the general noise model. So we work in formalism by Kitaev that has not been used very much, but this formalism of Kitaev is extremely general. So after some searching in the literature, we use it because it allows you to talk about encoding partially. So like going from a certain level of encoding, going up and going down. Okay. So normally if you, in the fault-tolerant literature, people go from classical, they encode it to something, or they decode it completely. But what we need in our work is that you encode kind of like you go from one code, you maybe encode it a level higher and you go down again, right? So you can switch from an encoding to a higher encoding and down. And Kitaev's formalism is extremely formal, which is very, very nice. It's a very long paper he wrote, but it's very good. And also it allows you to deal with very general noise, namely also coherent noise. So when your unitary is rotated a little bit, okay? This here was kind of like what people call a stochastic noise, where with some probability something happens, so you can still think of things being very classical, right? But if your error is of the type that instead of a certain rotation, you do a certain different rotation, then the error is not of this type, actually. It's just it's a different unitary you do that's close to the other one. So we can deal with that. And we also have similar statements for receiving information, etc. Okay. So I wanted to, I don't know how much I'm doing for time. It's pretty bad. A little bit over. How much can I go? 10 minutes, yeah, okay. So I want to give you a very quick idea because I think many of the questions address part of it. Yes?
Question, aside from this coding issues, do we know like how to even physically convert, I don't know, photonic qubit to superconducting one?
Oh, people are working on this.
Reliably.
People are working on this. And no, there will always be errors, right?
Yeah.
But I mean, we're trying to, this is the software solution to QSoft, I guess. I mean, this is a software solution to dealing with the errors that the experimentalists might not be able to fix. There's a lot of things they have to fix before we can use these theorems, but they don't have to go to zero error. Yeah. Okay, I want to give you at least an idea of the proof. Okay, so basically what I have to show is I have to massage the left-hand side, looks like the right-hand side, right? That's roughly the outline of the proof. So start with the left-hand side, you know the construction, I explained it. So, and then imagine that what I can do, of course, is I can do some magical imaginary object. I can do an ideal decoding where there's no errors happening, right? I can do an ideal decoding and I can do an ideal encoding afterwards, right? So the encoding, so here is my my logical qubits. I can do this ideal decoding, and this here is the syndrome information that I keep in yellow. Okay, so there'll be errors happening, and they're basically diagnosed by the so-called syndrome. Okay, so it's a bit like if you're in majority code, you would just remember where what your stabilizers were, right? That the error happened between the first and the second, and so on. So these are the syndrome qubits. And then when you get exactly the same state, when you take the syndrome qubits and you basically do an encoding again, and you basically inject the same errors again on your thing, right? So that's kind of like making this code encoding and decoding a unitary operation. And then I get the identity. So I'm just going to insert it here. Boom, everywhere, right? Very nice. Now note that when I now have taken, and I'm starting with classical information, right? And I encode it and I run my circuit, my state preparation circuit, and I'm now in this logical subspace. Now the definition of being in the logical subspace, or the definition of having something that is a logical qubit, the very definition of that is that if I were to decode it with a perfect decoder, I would get the perfect state. Okay. So if I look up to here, actually I have this perfect, my perfect psi. I'm sorry, it says encoded. This is the perfect state preparation. Does it make sense? This is actually really interesting. I mean, if you want to take some takeaway of it from this talk, then it's the definition of a logical qubit. Okay, so a qubit is somehow in the correct logical state if by a perfect procedure I can decode it. So that's the definition. So I get this perfect thing, but of course there is some syndromes here, and the syndromes are, these are the error syndromes. I put them on the side here, okay? These are the error syndromes. And now these guys here, this is basically like a perfect encoder with an imperfect decoder. Okay? That should be kind of like, what should this be? It should be kind of like a noisy channel, some sort, right? So I encode something perfectly, and then I decode it imperfectly, right? I do it separately for them. So that's pretty good. So these are, and this error syndrome here will be decoupled from the input. Let's not worry about that. And actually these ones here, these individual ones, they are basically, I mean, that's not so hard to show. It's also a paper by the Hordeskis from some time ago, that they are basically that the identity plus a little bit of noise. Okay, so that's not so hard to show. What is interesting is that the noise, it will be correlated because this error syndrome is a combined one for the whole thing. It feeds in all of them. Okay, so I have like some noise that's correlated. Oh, yeah. So it kind of looks like this plus some noise, and the noise gets correlated through this through these error syndromes. Yeah, and then, but you see that only with the probability delta something bad happens, and that you can now unfold into this a delta fraction has an error here. So you can somehow combine this into this, and then you obtain the result. That's the idea behind behind the thing. Maybe I go back and yeah, I guess. Yeah. So you sort of replace. You put this identity in. It decouples what you want from the noise, and then you have the noise here, and that's very good. And the noise is very kind of like mild noise or something. Okay. So that's it. Yes.
So this low weight noise is not necessarily IID. Is the point.
No, that's not IID.
Yeah,
No, it's not IID. And there is a bit of a difference in which noise models you work, and we can talk about. There's some more subtleties there, but yes. Here's an application, okay? And That was, of course, the original thing we started at some point with. Okay, let me show you this application. The application is as follows. I have a channel, some quantum communication channel. Think of a piece of fiber, glass fiber. I'm repeatedly allowed to put stuff through, but I'm thinking of it as having many small glass fibers and using them at once, okay? Using them once, or you can think of preparing something and using the one after the other. The standard paradigm for communication, so Claude Shannon, what you do is you put an encoder here that encodes, you have a classical input, you encode, you put through the channel, you decode, and that's your output. I need some notation here. You have M input bits and N channel uses. And then there is the capacity. The capacity says there shouldn't be an error in the output, okay? So probability that the input is not equal to the output should be smaller than epsilon. And what I want to push through is M divided by N. Okay, so I have M divided by N is the rate, right? The rate of what I can communicate via the channel. Okay, that's the capacity. It has a formula, but the formula is not so important for us now. Okay, and in quantum communication, it's the same. Okay, but we are talking about the classical, just to keep things simple, the classical communication over a quantum channel. Yeah. And there is also a theorem, everything looks the same, a theorem looks also very similar. Okay. So I have M inputs, I want to send them over channel, but the channel is now quantum, okay, here, quantum. This one here is still classical, but the encoder is still quantum. So this is the situation we had from before, right? So we want to do something with our thing. And I don't want to blow it up by a factor 49 or 7, right? Because I don't want, because my rate would go down by a factor 49 or, would go to 0. So I want to, if someone tells me, hey, you got N channels to communicate, and then I ask Polebo, Schumacher, Westmoreland, and then say, oh, but then you got to prepare those input states for the channel. Well, then I better go and do that, right? So then I go and try to do that, and it will not work. So I have to kind of make a fault-tolerant construction for this. And that is sort of what we've been trying to do. So, so this assumption of this noisy encoder decoder, which was sort of the main assumption, that somehow doesn't, right? That is not true anymore in the quantum case. And the first question you might ask, is quantum communication possible at all? And depending on how exactly you ask the question, the answer is actually not obvious. But in this particular case, it is not so hard to see that it's possible at all. But and the maybe more advanced question is, can I communicate at the same rate? Is the capacity formula continuous by switching on my my delta noise here? Okay, so from going from delta equal to 0 to delta equal to 1, it could be that my capacity just drops by a half. I don't know what. So is it continuous as I push the delta going to 0, push it down? And so we proved this little theorem some time ago. I made a, I think it's clear what I mean by a, this is just a definition, by a delta capacity. So if you, it's a capacity such that when my encoder and decoder are, get a delta fraction of noise on the like probability delta noise on the gates that they perform. What's very important for the definition is that the noise is not allowed to decrease with growing n. Right? Sort of we are in the spirit of a threshold theorem. We in communication you take block length bigger and bigger, and but you want to keep the error fixed. You want to be in this paradigm. Hey, someone please build a quantum computer. But then, I'm fine if you build it to that error. And now I want to use it. Okay, and there we could prove this. So we could prove, you can formulate it with a threshold, or you can just say the capacity at delta noise. So we make this fault-tolerant construction as before, that I showed you before, is actually bigger than capacity at 0 noise minus something small, and that something small goes to 0 as delta goes to 0. Okay, so we actually have a theorem that says, hey, the capacity is the same, it stays the same. Yeah, the level can depend on the n, maybe it's not so important. And the theorem before that I showed you before was kind of important for several reasons. That's why I separated. We now can do the construction now code by code, so not only for the capacity, but you come with some code. And then depending on what code that is, our construction works with that code. And it also works for general noise, also for coherent noise. So not only the stochastic noise. All right, I'm done. I think we have a new paradigm for fault-tolerant quantum input output. We think it's relevant. It does establish the quantum Shannon theory as the appropriate model. You might say if that theorem wasn't true, then there would be a problem with quantum Shannon theory because the assumptions might be unrealistic in some sense. It gives constructions, explicit constructions for experimentalists, but maybe we want to improve on those. In collaboration, maybe. And I do think there's this broader relevance. I mean, that's why we discussed. I mean, some of the details there have to be fleshed out on like how to use it in order to distribute computation, etc. But for this, yeah, maybe I should. One thing is that when I talk about communication, a lot of people think that things have to be very far apart, but that's not necessarily the case. Now, a lot of people talk about multi-core processors, in which case somehow communication is just something, you know, in a room or on a chip. And I think also this is, oh yeah, so, and of course they took a lot of issue at the second point here. It was a little bit when I gave the topic continuity. But maybe you don't. Thank you very much for that.